Geopolymers in general. Okay, so geopolymers in general are rock forming minerals. So they are produced when a aluminosilicate source, such as fly ash, is mixed with an alkaline activating solution. It could be like potassium hydroxide, sodium silicate, and many more. But for my project, I'm working with sodium hydroxide. So when you mix aluminosilicate source with alkaline activating solution, it forms a flowable cementitious paste. And if you leave it at room temperature or at near room temperature, it solidifies to give you a solid monolith, which is called as geopolymer. So geopolymers are considered as innovative and alternative material to the conventional ordinary Portland cement. So they are new in the industry, and the general formula is as shown here. And the formation of the final geopolymer product is very different from the cement hydration. So here what happens is like the fly ash, which comes from the coal power plant as an industrial byproduct, is when mixed with alkaline solution, it undergoes various processes such as dissolution, nucleation, polymerization, and finally when you cure it, you allow it to cure, it finally solidifies to give you a solid monolith. I will talk a bit about radioactive waste now. Like there is more than 1 billion tons of radioactive waste produced every year worldwide. So these radioactive waste are initially characterized based on whether they are liquid, solid, or gas, and also based on their half-life and activity. So my project is mainly focused on low level and intermediate level activity material, not on the high level radioactivity material. And so once they're characterized, they undergo a treatment process in which these wastes are concentrated or filtered out. And finally, they are conditioned. Conditioning means that those nuclear waste is converted into solid waste form by using processes such as cementation, polymerization, or geopolymerization. So once these nuclear waste are conditioned, they are stored inside steel drums or concrete drums and finally disposed in the earth repository. So among these radioactive waste, the one which contains cesium is of paramount importance because of following reasons. First of all, the half-life of cesium is pretty high. Like cesium 137 is 30 years of half-life, and cesium 135 has half-life of 2.3 million years, which is quite a lot. And also both of these cesium are has really long-term adverse effect on the environment. Also, they have really high solubility, which makes them easily leachable when they come in contact with water. And also they have high chemical reactivity. So because of all these factors, it becomes a very important thing to condition them really well. So the current cement, the current matrices that are being used to condition such waste are generally cement based, especially ordinary Portland cement, and also some cement polymer composites. And the other alternatives are bitumen and some phosphates. But generally the cement based materials are being used, and they have certain disadvantages, such as they are highly porous. They are comparatively easily leached. They have low thermal stability as well as poor acid corrosion resistance. And also it has been found that the retention of radionuclides in these cement-based matrix is not that ideal. So therefore, low cost sustainable alternative material is required for conditioning of such waste. So if we compare the candidates among each other, we see that like the geopolymer plays an important role and shows a lot of potential in terms of cesium encapsulation, and in terms of leachability as well. It performs better than other materials, and the water content can be eliminated, as well as they have excellent fire resistance. If we look into the advantages of using fly ash geopolymer in comparison to ordinary Portland cement, first of all, we are utilizing the industrial waste fly ash. More than 860 million tons is produced every year, and only less than 200 million tons is utilized. And these fly ash is very low cost and easily available as well. On the other hand, these fly ash-based geopolymer, once formed, have very reduced CO2 footprint by about 80% in comparison to ordinary Portland cement. Also, it has been found that they perform better in harsh environments and have excellent fire resistance, as mentioned before. And a few papers suggest that they have better encapsulation of several radionuclides within them from leaching point of view. And it has been demonstrated that in ordinary Portland cement, this cement is only physically captured or encapsulated, but in terms of fly ash geopolymer, it has been proposed that they form a chemical bond with it as well. So it's encapsulated both chemically and physically. If we look into the schematic of how the system looks like. So for my project, I'm using non-radioactive cesium in the form of cesium salt, which is cesium hydroxide. So if we look into the OPC matrix, it has already been proven that in the ordinary Portland cement, there is only physical immobilization or encapsulation of cesium. But if we look into the fly ash geopolymer, which could be amorphous or partially crystalline in nature. So if we look into the amorphous molecular structure, then we see that the tetravalent aluminum here is charge balanced by sodium, and it can be replaced by cesium plus ions as well. So which in terms will give it a chemical bond within the material and prevent cesium from leaching out. And also, once these geopolymers are aged or heat treated, they tend to form zeolitic phases within the material. So once these zeolitic phases are formed, they have really high adsorption capacity for cations. So, and also it has been found that these zeolites are formed in the pore structure. So if there is any excess cesium present in the pore, which is not reacted to the geopolymer, then it can be encapsulated within these zeolitic sites, so which can further enhance the physical and chemical immobilization within the material. And also it has been found that if there are in situ zeolitic phases present in FAGP, few studies suggest that they have beneficial effect on the long-term durability as well as compressive strength of fly ash geopolymer. And because of the presence of these in situ zeolitic phases, since they have high cation exchange capacity and adsorption capacity for cations, they have potential cesium encapsulation sites within, so which can be induced and tuned within the FAGP matrix to further encapsulate the cesium within the system. So here are some basic objectives that I'm working on. So first of all is to study the effect of different processing parameter of geopolymers, such as concentration of sodium hydroxide and various curing conditions, and cesium doses on the final geopolymer product form and on the in situ zeolitic phases, and how the cesium, how these processing parameters are affecting the cesium encapsulation within the matrix. And also other characterization includes slurry characterization, and finally when the products are formed, how the leaching behavior of cesium is carried out, and how the adsorption of the geopolymer is happening for cesium material. And finally, to relate the effect of these processing parameters with the microstructure evolution and the mechanical properties. So if we look into the flowchart of how my work is carried out, we see that I'm using fly ash and sodium hydroxide, and the cesium hydroxide can be added to the sodium hydroxide, which dissolves quite easily once you add it. So once they are mixed together, they can be characterized, like the slurry can be characterized based on flowability, setting time, or viscosity. And once they are allowed to set, they form fly ash geopolymer, which are inherently amorphous in nature, but with heat treatment and aging can have in situ zeolitic phases, and also which the whole system contains cesium waste. And so the material that is formed can be characterized based on compressive strength, porosity, microstructure, and finally some leaching test and adsorption test can be performed in these materials. And finally, the effect of in situ crystallization and the process parameter will be studied on the leachability of cesium and adsorption. So I'll briefly, so I will explain the few experiments that I've carried out, so which is dependent on the process development and test and crystallization of FAGP'S for waste encapsulation. So the materials that I used was fly ash, which had silica to aluminum ratio around 2, which is considered as really good for cesium encapsulation based on previous literature. And so I used this fly ash and mixed it with 8 molar, 5 molar, 8 molar, and 11 molar sodium hydroxide. I will refer it to as FAGP 5 molar, FAGP 8 molar, and FAGP 11 molar every time it comes next in the slide, which means that these geopolymers are produced using these alkalinity of sodium hydroxide. Also, the solution to solid ratio that I used was 0.4 based on the castability. It can be further improved, but like for the current scenario, I used it as 0.4. And I used non-radioactive cesium in the form of cesium hydroxide and varied it from 2 to 20 weight% of solid. So if we look into the ternary diagram of alumina, SiO2 and NaO2, so here is the range where my work lies in. And so the different specimens that were formed were cured at different temperature and different curing times, which will be mentioned in the plots itself. So if we first look into the compressive test strength results, so these tests were performed after 14 days total. So if we look at the room temperature cured geopolymers and OPC, we see that the geopolymer didn't attain their final strength after 14 days. But once they are heat treated at higher temperature, like 50 degree and 100 degree for a certain amount of time, they start to gain strength, which means like the geopolymerization process is expediting and the final strength is increasing. Also, it was seen that the 11 molar FAGP produced highest compressive strength. And if you look into, so these tests were performed after 14 days. And I led some of the samples the cure for 6 months, and I saw that there is a significant improvement in the compressive strength once they were carried out again. And the highest compressive strength was seen to be more than 56 megapascal for 11 molar FAGP, which was beyond the instrument testing limit, but that's the maximum the instrument could measure. And also for the OPC, the compressive strength increased. If we look into the phase composition by XRD plots of like these heat treated and cured samples, we see that a lot of different, so at room temperature, no zeolitic phase was seen in all different FAGP produced using different molarities. But if you change different molarities, we see that a lot of, and you provide them high temperature and curing time, you see that a lot of zeolitic phases can be formed within the material. And it was seen that for higher molarity and high temperature, you can achieve a specific zeolitic phase that you can target and use it to further study the effect of these zeolitic phases for cesium encapsulation. So, so since the hydroxysodalite phase could be formed, if we see it using SEM, we see that these hydroxysodalite phases are mostly present in the pore structure. If you can see here, so these are the hydroxysodalite phase. So if the cesium that was added initially is present within the geopolymer material, but if there is any excess cesium that is present within the pore material, then these zeolites has the capacity to absorb them even further and retain it within the material. So using that, like since I know that hydroxysodalite phases were formed, I tried to purchase some hydroxysodalite pure, but it was not commercially available. So I prepared it in the lab itself using a certain method. And so these are the pure XRD peaks of certain of the hydroxysodalite phase. And if we compare it with the geopolymer that were formed and has hydroxysodalite phase, we see that the peak of these phases match, and it could be used to quantify the amount of hydroxysodalite within the material. So and the sodalite framework looks like this. So it generally has like cages and molecular sieves, which are like cesium, potential cesium encapsulation sites within the material. Also, as I mentioned that at room temperature curing after 14 days, no zeolitic phases were formed. But if you leave the material to slowly crystallize for 6 months at room temperature, it was seen that some of the primary gel of geopolymer, which was initially amorphous, starts converting into crystallized phase, which is the crystallized NaSH phase, and it could be seen here. And it could be further utilized to study whether these phases are helpful for cesium encapsulation or not. Also, I conducted few pH measurement tests using water as leachate, and I measured the pH of these geopolymers that were formed within the material, and it was seen that like the 14 days cured geopolymers leaches a lot of hydroxide, maybe because of incomplete geopolymerization. And but after 6 months, the pH goes down around between 9 to 11, and it can be seen here, which shows symptoms that that the geopolymerization process is moving forward and the material form is getting stronger. So from here, the general conclusions that can be drawn is that the compressive strength of the material and also the in situ crystallization phases definitely depends on the concentration of the activating solution and also on the curing conditions provided. So based on that, the geopolymers can be channeled. And also the room temperature cured specimen initially showed no zeolitic phases after 14 days. But once you leave them to slowly crystallize, after 6 months, they start to form partially crystallized FAGP phases. Also, only hydroxysodalite phase were present at high molarity and high temperature within geopolymer pore network, not on the primary gel. So these hydroxysodalite phases can be targeted within the material and can be crystallized in the FAGP material and can be studied for cesium encapsulation. So once these tests were conducted, I came to conclusion that if we leave the material for longer period of time, we start to gain strength as well as a certain crystallization happening within the material. So I used the samples that were cured for 6 months at room temperature for the leaching test as well as the adsorption test. So if we compare the leaching of cesium from these fly ash geopolymers, so I followed a standard called ANSI 16.1, which is well known among nuclear society. So which was conducted to see whether how the cesium encapsulation is happening within the material. So if you compare the fly ash geopolymer with the OPC, in both of these, the solution to solid was 0.4. So if you compare them both, you see that the fly ash geopolymer do not leach out cesium very like negligible, and but for the OPC it leaches out cesium a lot. And if you compare different geopolymer among themselves, all of them perform way better than the OPC. If you look at the scale, it's varying from 0 to 3, and here it's varying from 0 to 160. For OPC, it leaches a lot, but for different geopolymers, all of them perform better. And like if you see here, the cesium dosage was 2.8% in solid, which is around 20,000 ppm in the material itself, and only less than around 0 to 2 ppm cesium was leached from the geopolymers, which is quite significant. Also, based on these results, and you can calculate the effective diffusion coefficient, and from there there is a term called leachability index, which gives the ability of a material to encapsulate the radionuclide within the material. The higher the value, the better it is. So the threshold value for leachability index is 6, but the higher the value from 6, the better the material is. So if you look at the values here, the fly ash geopolymers have really high value in comparison to OPC. So which proves that these geopolymer, even having different molarity of sodium hydroxide within them, they perform really well in comparison to ordinary Portland cement. And among the geopolymers itself, the 11 molar produced geopolymer are performing better. And also, so based on that, I use 11 molar geopolymer for my further studies rather than studying all of them. So for the 11 molar sodium hydroxide produced geopolymer, I also tried adding like 28% of cesium in them, and it could be seen from the plots. So both of these plots belong to OPC, cured at different times as mentioned here, like 14 days and 6 months, and 28% and 28%. And here as well, if you compare these geopolymer with the OPC leaching, then we see that OPC leaches a lot of cesium rather than fly ash geopolymer. So even if you compare ordinary Portland cement with 28% cesium and cured for 6 months with fly ash geopolymer, which was cured just for 14 days and with 28% cesium, it still performs way better than OPC. So which is a sign of a good encapsulation capacity of fly ash geopolymer. Also, to like understand whether like heat treatment of geopolymer is better or worse in terms of cesium encapsulation, I heat treated. So one of the sample is cured at room temperature for 6 months. Another sample was heat treated for 100 degree for 7 days and kept for a total of 6 months. And if you can see that the heat treated sample started to form crack, it is because the material was not in a closed environment. So because of the water evaporation, it led to a lot of crack formation. But even then, if I conducted the leaching test, I see that the one with cracks has some hydroxy sodalite phase, and it doesn't perform as well in comparison to the non-cracked sample. But still, both of these samples perform way better than OPC if you look at the scale here. So here I was trying to understand the effect of hydroxysodalite phase, but I couldn't study that because of the cracks formation. So like there are certain experiments I'm conducting in which I'm trying to avoid cracks and then perform the experiment to see the effect of hydroxysodalite within the material. Also, as variation in these FAGP metrics, like the 11 molar sodium hydroxide produced, I tried to, so I already discussed the gray and the red ones, which were like cured at room temperature and at 100 degree. So I also tried uh, heat treating the same sample for at 800 degree for 7 days. And it was seen that the concentration of cesium leached even improved, like the value went lower. And so basically when you heat treat the sample at 800 degree, the whole product converts into a new phase, which is called the naphthalene phase. And if you see the pH of the leachate, it also falls in the acidic region rather than initially as it was in the basic region here. And also I tried to add or dope 4 weight% of hydroxysodalite within the geopolymer material, and which was cured at 100 degree just for 20 minutes. And I tried to run leaching test on them just to see whether doping helps or improves the cesium leachability. And it was seen that it doesn't perform that well, like it leaches. Maybe it's due to the reason that the the geopolymer were not cured for a longer duration of time, just for 20 minutes at 100 degrees. So it is a possibility that the proper geopolymerization didn't take place, and hence the cesium is leaching a lot. But still, if you compare every of the different variations of geopolymer with OPC, all of them are performing way better than OPC. So the general conclusion that can be drawn from here, that under all conditions, FHGP are performing better than OPC or cesium encapsulation. Long-term curing at room temperature, like the slow at room temperature and the slow crystallization alloying, um, leads to higher compressive strength with time, as well as less release of OH minus ions in the leachates. And finally, the partial crystallization of the amorphous NaSH phase is taking place within the geopolymer. And so the effect of, and also the effect of hydroxysodalite could not be studied because of the crack formation here. But I found a method, like I tried to prepare geopolymer in a closed environment, avoiding thermal shock, which leads to no crack formation within geopolymer. And I will use this, the material prepared in my further experiments to see the effect of hydroxysodalite, whether it helps in cesium encapsulation or not. Also, like after leaching test, I performed some adsorption tests. So all the adsorption test materials has no cesium in them. So the cesium uh, is present as a feed solution, and then you make a powder out of your binder, and then with different doses or amount of different cesium or different binder content, you see how much of cesium is adsorbed within the material. So that's how the percentage cesium adsorbed can be calculated. So based on like the adsorption kinetics, I haven't included the models here, but a lot of information can be derived out of them. First of all, if you conduct adsorption kinetic studies, you can understand the mechanism that is happening, and also the rate of adsorption process. And also we can determine whether it's a chemisorption of the material of the cesium within the material or physisorption. And from adsorption isotherm studies, we can understand the distribution of uh, adsorbate molecules which are present under equilibrium conditions. And based on these isotherms, a lot of more information regarding whether there are homogeneous sites and monolayer adsorption or heterogeneous surface or non-uniform distribution. And after the model fitting, type of isotherm and degree of heterogeneity of the adsorbent can be determined quantitatively as well. So here are few batch adsorption studies results. So initially I compared fly ash, OPC, and geopolymer that were cured at room temperature and 100 degree for 7 days. it can be seen that for OPC and fly ash here, for OPC, the amount of cesium adsorbed is almost negligible, almost zero, which shows it doesn't have any adsorption capacity for cesium. For fly ash, even it is still low. And if you look at the geopolymer here, which were cured at 20 degrees just for 7 days, it starts to adsorb cesium within the material. But here, since the geopolymerization process is not complete after 7 days, we can see that it's not that significant, the cesium adsorption in the material. But once you cure it at 100 for 7 days, which further increases the cesium adsorption, which further increases the geopolymerization within the material, we see that the cesium adsorption increase here. And so these studies were conducted after 7 days, but the same material was left for 6 months, and the effect was seen on the adsorption capacity for cesium. And here there are different binder content that I use of this material. So for example, so this material, the blue curve, was cured at 20 degrees for 7 days. Here, if you see the gray line, this is the same material which was cured for 6 months. And we see that even with low amount of binder content, the cesium adsorption is increasing tremendously. Like here, like I haven't used the 1 gram value, but still, like you see that even at lower values of binder content here, the cesium adsorbed within the material is quite higher. But it was also seen that once like it was heat cured at 100 degree for 7 days and left for 6 months, the value is almost in the same region where it was supposed to be, between 30 to 60% adsorption. So the value is still in that region, but this kind of shows that the presence of hydroxysodalite within the material kind of decreases or doesn't affect too much the adsorption of cesium within the material. But if you have a crystallized zeolitic NaSH phase that is formed from the amorphous geopolymer phase, then it kind of helps or improves the cesium adsorption capacity within the material. And also, like as a separate test, I also perform adsorption test using hydroxysodalite, and it was seen that only 18.3 of cesium is adsorbed using pure hydroxysodalite. So all the conditions were same, so it can give a really high relative comparison of how the materials are behaving within the system. And also, like the effect of different pH was seen, whether how the material is performing at different pH. And it was seen that that the heat treatment of the geopolymer definitely decreased the cesium adsorption at all different pH, as was seen here as well. Also, like presence of NaSH zeolitic phases, as I mentioned before, is improving the cesium adsorption within the material. But like generally but it can be seen that both of them are way better than OPC, which was almost negligible. So even with like presence of hydroxysodalite within the material, we are seeing that we are going towards the basic reason. The cesium adsorption is increasing from 30 to almost between 30 to 60%. But for the geopolymer with some amount of crystallized NaSH phase, the performance is even better. So the general conclusion that can be drawn from here is that FAGP is showing significantly better performance for cesium encapsulation in terms of cesium as well as adsorption of cesium. The fly geopolymer properties improves at room temperature curing in terms of compressive strength and cesium adsorption capacity. Also, the presence of hydroxysodalite depicts reduction in cesium adsorption capacity, as was seen before on the plots. So the next step is to use these data and to optimize them to an equilibrium state, and then fit them in the models to derive the information that I discussed before, that can be drawn from these models. So apart from this, the further studies that I'm planning to do is the study the leaching behavior of fly ash geopolymer with different curing times. Like I conducted the test for 6 months for the geopolymers cured for 6 months, but I want to see the effect of how different, like how the microstructure change with different curing times is affecting the cesium encapsulation, and also like varying the different hydroxysodalite contained within the material. Also, like leaching studies varying cesium doses is also my plan of work. Like that's what I'm aiming to do as well. And finally, to quantify these phases using XRD, and also to determine degree of crystallinity within these material, and to work on the kinetics of in situ crystallization of NaSH gel as well as the hydroxysodalite within these material, and then further relate these to porosity and density of these system with the final properties that are being attained. So for that purpose, I'm currently running DOE, which is like a regular 2-level factorial design. So I'm using 4 different variables, which is sodium hydroxide concentration, cesium doses, curing temperature and time, and setting them at low and high values. And finally, deriving the output out of them, and then finally finding the correlations between the outputs and the initial process parameters. So this is the plan for the future. Thank you so much for listening. I'm open to questions now.
Thank you. Wonderful. Very good. Excellent presentation, Shubham. And we can open this up for discussion.
Yes.
Any questions for Shubham? Obina. Please unmute yourself, Obina.